This is FRM Part 1, Book 2, Quantitative Analysis, and the chapter on Regression Diagnostics. Let me quickly remind you where this chapter fits in with our recent discussions and recent chapters. We've talked about a multiple regression model. And so let's come up with just a quick model here. Let's suppose that we're trying to figure out whether Moody's or Standard & Poor's or Fitch is going to change the credit rating on a particular bond issue. And let's suppose that we gather lots and lots of data. So our dependent variable is going to be, let's call it a change in default risk. And we'll collect independent variables for lots and lots of different bond issues. And of course, we collect data on things like, cash flows and probably some leverage ratios and maybe some leadership things and probably general levels of interest rate and, maybe 5 or 6 other kinds of variables. So we put those into our Excel spreadsheet or some other kind of a software package, and it's going to produce a regression output for us. And we'll go ahead and look at the R-square and look at the F to try to see about the entire equation, and then we'll look at the individual slope coefficients and their statistical significance, and we'll try to make some conclusions about our model and then about changes in default risk. Well, this chapter really could be called, What Could Possibly Go Wrong? We have these assumptions of the ordinary least squares model, and if those assumptions are violated, then the conclusions that we make based on that regression output may or may not be valid. And so you'll see this as we look at the learning objectives here. We'll talk about heteroskedasticity. We'll talk about multicollinearity. We'll talk about having too few independent variables and too many independent variables. We'll talk about some bias. And then at the very bottom there, we've had some discussions on that characteristic that we called BLUE, the best linear unbiased estimator. So let's go ahead and start with one of the big problems, heteroskedasticity. So I want you to look in the very middle of the slide. One of the assumptions of the OLS is that the error terms have a constant variance. So look under homoskedasticity, there you'll see the sigma squared, right, with no subscript. And that means that there is a constant variance that arises from a regular old linear regression model. Heteroskedasticity, on the other hand, is when those variance terms, those error variance terms, are not constant. In fact, they're dependent on each individual observation. So look at the bottom right there. That's why I have sigma squared with a subscript. All right. Now, looking at it in that form is probably not too much of an indication of what the problem with heteroskedasticity is, and that's why I have a good picture here. So look at the relationship between our independent variable x and our dependent variable y. There's our black bolded upward sloping line from our model, and notice that the error terms, some are above, some are below, but they're not too far apart. That kind of looks like they're going to produce a constant variance. But now look under heteroskedasticity, you see kind of a cone shape, so that as we get higher and higher levels of the independent variable, then who knows what we're going to get with the dependent variable. So there's a cone shape out there. Common causes of heteroskedasticity is if you don't have a complete model, or if you have a small data set and you have some outliers. Now, of course, the question is, all right, what's the big deal? So what if we don't have homoskedasticity? Well, we can't really say so what, because there is a big problem. What happens is that these OLS estimators, they no longer become efficient because there's some other estimator out there that has a smaller variance. What that means then is that it's going to produce incorrect standard errors, which means when we do the confidence intervals and when we do some hypothesis testing, we're going to divide by those standard errors, and those conclusions are going to be, geez, at the very best, misleading, and at the very worst, useless. So the question then becomes, if you suspect that heteroskedasticity is causing problems in the model, then the first thing that you need to do is put some scatter plot together like we did in the previous example. But, let me just swing back here quickly. If you look at it like that, clearly any researcher is going to say, oh yeah, that looks just like heteroskedasticity from every textbook that I ever looked at. But sometimes it's not quite as obvious. So we need some kind of a statistical test. And there are several of them out there. But the white test seems to be about the best one because it allows for nonlinearity of those error terms. And then it's better able to capture whether or not, here, let me go back here real quick. It's better to capture whether those cone-shaped outliers are in fact enough away from the mean or that line to cause problems. Now, the white test is relatively straightforward. What you do is you go ahead and just estimate a set of linear parameters for the model, and then you regress the squared residuals on a constant and then all of the explanatory variables. And then what you do is you look at the cross product of all of those independent variables. And the result is that if the data is homoskedastic, then the squared residuals will not be explained by any of those variables. Otherwise, the data is heteroskedastic. And then the question is, well, what do you do with it? And I learned this back in graduate school. I mean, one of the first things that we learned in my first doctoral level econometrics class, once we got into the OLS regressors, is my professor told us how weak this method was in handling all these kind of problems out there. So we did weighted least squares. In fact, my dissertation used the weighted least squares. So you just divide the regression equation by the standard deviation of the residual. And so you should remember we did that with covariance, right? You divide by standard deviation. When you calculate a beta, you take the covariance and you divide by the variance. And so dividing by standard deviation is a really, really good way to try to help either narrow things down or to eliminate some problems. So my experience was to use the weighted least squares method. But you can also transform the data by taking the log of the data or dividing the data by another independent variable, or you can even use weights before you estimate those parameters. Of course, if you're asking for me, I would vote for method 1, just because that's pretty much the only method that I ever did. However, those other two methods, they have their values. The next problem is multicollinearity. Now remember, go ahead and look at the very bottom there. Look at that regression model. So we have y is equal to or dependent on 2x variables. Now remember that these variables are called the independent variables. That means they cannot be dependent on each other. I mean, it sounds silly and it sounds simple, but it's actually true. So how do you tell whether those two variables are dependent on each other? Well, of course, you look at the correlation coefficient between them, right? Ideally, those independent variables would be completely and totally independent. That's not a statistical term, by the way, which means they would have a correlation coefficient or a covariance of 0. But the reality of life is that variables are related and they're interrelated and they're correlated in all different sorts of ways. So you're going to deal with some level of dependence, but we need to make sure that it's not too dependent so that it causes problems. Now, perfect multicollinearity is a scenario under which the two x variables are perfectly linear correlated. Let's take just a quick example. Let's suppose that we're trying to determine the returns on a portfolio of call options. And we put a bunch of call options in there, and one of our x variables is the return on a call option that is written on a particular stock that matures in 1 week, and another variable is a particular call option that matures in 2 weeks, and it's written on the same share of stock. So you have a call option and a call option written on the same share of stock, and the only difference is the time to expiration, which is, let's say, a week or so. And I mean, those things, they're probably not going to have a correlation coefficient of 1, but it's going to be pretty high. So when you have that kind of a scenario, when it's perfectly and completely explained, then you really don't need both of those independent variables. You only need one. Boy, there's an example of perfect multicollinearity, right? We got x1 on the vertical axis, x2 on the horizontal axis, and they are perfectly linear related to each other. So you don't need both, right? You don't need both. You only need one of them. All right, so let's go ahead and look at the consequences of perfect multicollinearity. And this is really an extreme case. When you have perfect multicollinearity and you throw this into Excel, Excel will print out a message that says something like, "Dear Mr. or Mrs. Researcher, you have no idea what you're doing because the independent variables are perfectly dependent." And so you'll get some kind of an error message. Now this, of course, is really interesting because this occurs at the extreme. Well, what we're trying to do here in these next slides is we're going to look at imperfect multicollinearity. How close do we have to get before it starts causing problems? So look at the solution that I have written there at the bottom. One of the collinear variables must be dropped. They are essentially identical anyway. All right, that should make perfect sense. Now, how about imperfect multicollinearity? So these are when two or more of the independent variables are imperfectly linear related. All right, and so look at the graph down there. You got x1 and x2. There's the line. And so, boy, it just looks an awful lot like, when x2 goes up, x1 goes up, and, they're pretty close. Now, it's not perfect, but they're close enough to probably cause problems with our estimators. Now, high correlations among the independent variables, of course, that suggests multicollinearity. However, the absence of high correlation or the presence of a low correlation doesn't necessarily mean that multicollinearity is not present. All right, so notice what I have in that second circle point. I said this just a few moments ago. All variables are correlated to some degree, even if completely at random. So it's a question not of how much multicollinearity exists, but really whether any multicollinearity exists. All right, how about the consequences here? Estimates will remain unbiased, and that's okay. However, the variance and the standard errors will increase. All right, so imagine you're going to divide by a standard error that's higher than what it ought to be. And so it's hard to distinguish the effect of one variable from the effect of another variable. And so we're more likely to make these large errors. And what that means then is that the t-scores and then your conclusions about whether the slope coefficients are statistically significant will be underestimated, right? That should make sense. Now, the other complication here is that those estimates that we come up with, they will be very sensitive to changes in specification. In other words, if you drop a variable or you add a variable, then those coefficients can change dramatically. And I remember in graduate school, we had really fast software back in those days. I can't imagine how fast it is today, but we would easily be able to change some variable and add a variable and transform a variable, and we would just fool around and see what the results were going to be. And clearly when there's multicollinearity, there's high sensitivity. Yeah, this one seems kind of like an obvious notion here. Look at the bottom example I have before I give you some definitions up at the top. Let's suppose that our regression equation is trying to explain the growth rate in GDP. So we collect data on things like interest rate and inflation and exchange rate. All right, so that makes perfect sense. Those three variables ought to do a pretty good job of at least beginning the explanation of GDP growth. Well, suppose you leave one of those out. Well, clearly, if you leave one of those variables out, you are not going to have a model that does a very good job of explaining the variability in the dependent variable. And that's what this omitted variable bias is. When a statistical model leaves out one or more explanatory variables that has a significant effect on the dependent variable. All right, and so this has two scenarios. The omitted variable, it might be correlated, but it might be a determinant of the dependent variable. And so both of those scenarios will cause problems. Now, when an omitted variable is excluded, then the assumptions of the regular old OLS that we've talked about so far are violated, or we're under-specifying the model. Now, the OLS estimates they're going to be biased, and they are going to be inconsistent because the estimated residuals are going to be larger in magnitude than when the true shocks actually appear. And so our model, look at the bottom there, we only have one independent variable when the true model is two independent variables. And so there's no way that our model is going to capture the reality of the relationship and the variability in that dependent variable, the y variable over there to the left-hand side of the equal sign. Now, another game that we played in graduate school was to let's throw in another variable. What happens if I put in the number of clouds in the sky in this model that's trying to predict stock returns or GDP? Or, the number of times one of our professors would look at us and say, you know what, you really don't know anything about econometrics or finance. We could put any number of variables in there. And what happens? Well, you guys should know this from previous discussions, is that the R squared of the model, it's going to get bigger and bigger. So it kind of looks like we're explaining those things, but they make no economic sense at all. So an extraneous variable is one that is unnecessarily included in the model, whose actual coefficient is 0, and would be consistently estimated to be 0 in large samples, like number of clouds in the sky as it relates to stock returns. And so this extraneous regressor then just has the opposite effect. And so note, I can swing back here. Here's the omitted variable, and then here's the extraneous variable. So what we're doing is we're just throwing another variable in there to see if it improves the quality of the model. Now, I did say earlier that the R square is probably going to get bigger and bigger whenever you throw these extra variables in there, but that's why statisticians are really, really smart, and they said, R square, that's a good starting point, but why don't you just ignore the R square and look at the adjusted R square, which adjusts for the number of variables over on the right-hand side of the equal sign. And so what happens is that when we threw that number of clouds in the sky into our model, R square goes up, but the adjusted R square goes down. And so that's really a test of the extraneous regressors. Yeah, now I love this explanation because for those of you who have been listening to my videos for a while will know that I try to use economics as part of my parenting model, and I do this to my children all the time: marginal cost versus marginal benefit whenever they are making a decision. And so this is exactly what we have here. What we want to do is we want to have the perfect model, right? The perfect model. But it's virtually impossible to come up with a perfect model. Sometimes our model is going to have too many variables. Sometimes it's going to have too few variables. All right. So what we want to do is we want larger models, right, to have a lower bias. But when we have these larger models, we have an increase in the estimation error and less precision in those parameter estimates. So it's really a trade-off, right? Do we want lower bias or do we want a lower estimation error? And so this is where my professors in graduate school, used to tell us that this comes from practicing, it's no different than shooting foul shots over and over again so you can make them in the pressure of a game. So you practice with these models, you come up with these models, and that's why we had all of those classes, and that's why we wrote dissertations, so that we could practice and get some experience and try to determine what's that best model. Now, of course, there are some formal ways to try to come up with the best model. So method 1, general to specific model selection method. So this is when you start with a large general model that incorporates all the relevant variables. So if you're trying to predict changes in GDP, not only do you include things like interest rates and inflation and exchange rates and the labor participation rate, but then you include other things like maybe the balance of payments, and then maybe the specific exports to a certain country like Canada, and then maybe the return on a call option written on a share of stock on a defense industry that has substantial contribution to GDP, and. So you start with all of these relevant variables. So let's just take an extreme example. Let's suppose you have 20 of these variables over on the right-hand side of the equal sign, and then we run the regression analysis and see how many of them are statistically insignificant. And then we remove those insignificant variables and then rerun the model using the remaining set. And then you remain and you reduce and you reduce and you reduce until all of the statistically insignificant variables have been eliminated. And that, I always scratch my head with that. That's supposed to lead you then to the perfect model. But what that ignores then is how those remaining variables then may have related to some of those other variables, and maybe those are important. So even though some of those variables are not statistically significant, maybe they're important. Of course, maybe they're not, and that's what the experience comes from. All right, how about method 2, the M-fold cross-validation method? All right, what we're doing here is we're going to choose the model that's best at fitting the observations that are not used to estimate those parameters. All right, so we have this huge data set, so we shuffle it randomly, and then we split it into M groups. All right, then we estimate the parameters using M-1 groups to make up what's called the training block. And then that excluded block is the validation block. And then we go ahead and use that excluded block to compute the residual variables. The residual values, and those residual values, they become the out-of-sample residuals. What we do then is we repeat that M times, and then we compute the sum of the squared errors, and we select the smallest out-of-sample sum of the squared residuals. How about moving on to outliers? Clearly, there's a problem when you have data that looks like this. I'll just go like this. So you have data that when you look at the X and the X1 and the X2 and the X3 and the X4, and then you're looking at Y, you think, okay, that sounds reasonable. But every once in a while, you're going to have one that says, oh my gosh, it's way up here or it's way down here. Call that an extreme case. All right, and so look at the picture there. If you look at the regression without the outlier, that looks like probably a reasonable slope given those, 1, 2, 3, 4, 5, 6, 7 observations, right? The blue flatter slope. But if you throw in that 8th outlier part of the sample, notice that the slope of the line increases and you get the red line, and the red line doesn't seem to match up with all the data. So do you see how an outlier can skew the slope of that line? So that's going to skew the beta estimates in the regression analysis. So the question then becomes, let me go back here. If we look at the outlier, we can clearly see that that's an outlier. So then we have to ask ourselves the question, all right, what's the easiest thing in the world to do? The easiest thing in the world is just to say, okay, let me close my eyes and my ears and my mouth and just pretend that that thing doesn't exist. Let's just remove it. Well, In a lot of cases, that might be an obvious notion, and if the sample sizes are large enough, eliminating that outlier is probably not that big of a deal. However, there has to be a statistical test. All right, so this is what Cook's distance does for us. It measures the impact of dropping a single observation. And of course, as you can guess, that when the sample size is relatively small, let's say 15 or 20 or 25, that outlier is going to have much more of a dramatic impact than if you have 500 observations inside of the sample. And so there's Cook's distance, there's the formula, and you might want to look at that just a little bit quickly just to remind yourself that this is really no different than anything we've done in stats all along, right? So look at the denominator first of all. We take the number of coefficients and we multiply that by a variance. All right, so we're used to dividing by a variance, so that shouldn't be any kind of a surprise that that's the divisor. But look in the numerator. What we're doing is we're squaring a distance, right? So we always square things to get rid of the negative. So what are we doing? We're squaring the distance between our regular y hat, which is the output from the estimated model, right? And the distance between the y hat raised to the minus j, that's when the value of j is excluded. All right, so look, if I were to exclude, let's look at, forget that outlier up there. Suppose there's just seven observations, and I exclude that one there that's really, really close to the blue line, right? If I exclude that one, what is that Cook's distance going to be, right? We're just taking a little teeny weeny distance, and even when we square it, that's not going to have any impact, right? But if we include that outlier out there into the model, including 8 of these observations, and then we exclude it, we're going to get a big distance, right? So that's really what we're trying to do with Cook's distance. And here's an example here. There's some X and Y's. I think this is study time and output on maybe an FRM mock exam. So we've got 6 people, and what did they do? They study a couple of hours and they get this test and test results. But look down at the bottom. This poor person, he studies way more than anyone else does, and he or she gets the worst grade out there, right? So what do you do? What do you do with that outlier? Do you just say something like, well, maybe that person, when he or she was studying, was also watching television or doing something else instead of focusing. And maybe those other 6, they were laser focused on their studies. There are all sorts of issues that can arise with these different cases, in this case 7, or the observations. All right, so this is what we do here. We're going to calculate that Cook's D. And, the standard is that if the distance turns out to be less than 1, then you're okay. If it's greater than 1, then you should go ahead and eliminate it, which was the case here in notice the red row at the bottom. Let's go ahead and finish up this slide deck. What conditions are the OLS estimators the best linear unbiased estimates? All right, and so the following conditions have to be met. The parameters being estimated must themselves be linear, right? So that's why it's called the linear estimates, right? The data must have been randomly sampled from the population, right? You can't look at the population out there and just pick, this little sector or this little corner right here. They have to be randomly selected. All right, non-collinearity. The regressors being calculated should not be perfectly correlated. All right, the regressors, they can't be correlated with the error term, and then the variance has to be constant. And I think that takes us through all of our learning objectives, and we addressed all those. Have a great day.